What happened? Oh, welcome everybody. So, my last installment for the live, and I think of the last live that I did, I said it was the last, and I kind of totally forgot about our second quiz that we have. So, what I want to do in this quiz is cover graphing trigonometric functions. We're going to deal with graphing sine, cosine, tangent, as well as the reciprocal functions. And you can see here on this quiz, I have four examples, four examples that we're going to kind of cover. And, really I'll sketch the graph. I didn't ask my students to graph it on the quiz. However, upon grading the quizzes, I think that probably would have been helpful for all of those that did graph it or did not, as far as identifying the characteristics. And then what I did is I just have some nice little multiple choice here that we will kind of end the live stream with. So we're getting into the last couple weeks here in my class for pre-calculus, and so this is the last quiz that they're going to take, and then obviously we're going to have a chapter test and then a semester exam. So coming up I will do one more live, I think a live stream I'm going to do. I have a kind of review that I'm going to set up. So for those of you that are still not taking an exam, then hopefully you'll be able to benefit, from on there. So, but basically what I want to do is just kind of cover these problems on this lovely Sunday afternoon, and then obviously if you guys have any questions throughout the live stream, make sure you guys are in the chat. I can see Destiny, Emily, and Colleen already here. So can't see it. Well, it's blurry. So thanks for letting me know, Colleen. Is that me, or is that obviously the screen? So just kind of let me know, because obviously I am running on Wi-Fi. It looks like my stream health is good though. So just kind of let me know as that goes if I can get anything else. I don't know why from there. Yeah, everything looks good on mine. So Kitty Gamer, hola. So how are you doing? All right, so just make sure everything else, I'm seeing not really any problems here with my stream. So, but if you do have any other issues, let me know. All right, thanks so much. I will go ahead and get started then, not waste any more time. Let's go ahead and attack these problems and kind of see, how I approach them in my class, and then hopefully that can help you out if you have any of these problems coming up. And so a lot of, when I'm looking at these problems, the main important that I want to talk about is, when things were applicable. So only going to talk about things where we can see there's a transformation, and one thing I did leave off was reflections. All right, so the main important thing though is we've talked about all of these is identifying basically what's happening to the graph. And we use kind of like for the sine function, it doesn't matter if it was sine, cosine, tangent, cosecant, secant, or cotangent. But basically we had these values, y equals a times sine. Oh, my pen is it's on its last legs, x minus c plus d. Okay, and again, you can replace the sine with any of the trigonometric functions. But the main idea is understanding what a, what b, what c, and what d is going to do to the graph. So, if we recall, for sine and cosine, A is going to be our amplitude. It's still a vertical stretch of the graph, but we use that as far as our definition. Can't write today. That is going to be our amplitude, which is absolute value of 2, which is just going to equal 2. The period in this case is going to be 2 pi divided by b, if you remember. So 2 pi divided by, in this case, we can see our b is going to be 1. So therefore that is 2 pi. And then you can see we have a c, which is going to be our phase shift, previously known as like a horizontal shift to the right and to the left. So I'm just going to abbreviate that with a p dot s, and that's going to be right pi over 4. Let's zoom in here for you. And then obviously we're subtracting a 1 on the outside, so that is going to be a vertical transformation, also known as a vertical shift. And we'll just say down 1. Okay, so basically, this is really the exact same thing as what we've covered from transformations of functions in our functions unit. And then we really just kind of introduced two vocabulary words, basically our amplitude, our period, phase shift, and vertical translation. But basically, as long as you understand what is your A, your B, your C, and your D, you can kind of label what the characteristics are, the transformations. There is obviously no reflecting because that would be multiplying by negative, so we don't have that case in here. But the one that kind of gets to us, which I think is the most confusing one, is talking about the domain and range. So what we're going to do here, or what I'm going to do, is just kind of sketch the parent graph or the initial period of this graph, because we know obviously the graph is going to repeat indefinitely, right? So let's just go ahead and graph the initial period of sine 1 to negative 1, and then we know it's going to complete a period in 2 pi and cross that pi. And then I'll have a maximum up here and a minimum down here. And again, this is just a rough sketch of the graph, just so you can get an idea of what it would look like. Really bad, but whatever, we'll work with it. So now let's go and take a look at, what has really happened with this graph. The amplitude is basically that half distance from the max to the min. So what that's done is that stretched it. So now the graph is going up 2 and down to 2. And then also the graph is being vertically shifted down 1 unit. So so now the graph goes, up to 2 and then down to 2, right? But then we've also now shifted the graph down 1. So now it's going from here all the way to here. Oops, wait a minute, down 2. Yeah, so I got to go down 1 more. And then it's going down to this point and then over there. Okay, and then so you can see I'm just dealing with the vertical transformations right now. I kind of forgot to tell you about that. So let's just look on the vertical transformations, because you can see on these on the vertical transformations, the range was originally -1 to 1, right? But then it got stretched from -2 to 2, but then it got shifted down 1. So you can see now that the range is from -3 all the way up to 1. So I'm just going to write here the range. And again, they are including those values. So that's going to be from -3 to 1. Now, the reason why I did domain second is obviously this graph is definitely being shifted pi over 4 units to the right. So that's just going to be a little bit of a shift over here. So you can kind of see, like, if you needed to graph, a rough sketch, it's basically the exact same graph, just kind of being shifted over pi over 4 units. And again, I wasn't really big on the graphing portion, so we didn't talk about finding the new values and stuff like that. But basically, you can take all these points and just add pi over 4 to them if you need to find new x-intercepts or maximum minimums, if that's something that's required in your class. But the main thing here is, if we're looking for the domain, remember this graph continues, right? It continues indefinitely to the left and to the right. So the domain for sine and cosine is all real numbers. So even though we wanted to label there's a shift going on, as far as the domain's concerned, it's not going to affect the domain. So the domain is from -infinity to infinity. All right, so now let's go and look on the next one here, which is the cosine. Now again, cosine is very similar to the sine, so we can automatically know, looking at this, we're going to have an amplitude, which is the absolute value of A, and we know the domain is all real numbers. So those are kind of some things that when I look at sine and cosine, that I'm like, I remember, those two things. We still have an amplitude though. And notice that we have a negative here, and that's why the definition of the amplitude is the absolute value of your first A, which in this case is A here, -1, so that's just going to be 1. Now notice we don't have our B in terms of this B times X minus C. So what I'm going to want to do is I'm going to factor out the B. So when I factor out the B, I'm left with, and I'm sorry, my pen is like at its last life, so I'm going to have to replace that. So that's why it kind of is, some of my writing's not so great. So when I factor out a 2, I get x plus pi halves. And again, you can check my work. And basically what I did is I divided a 2 from 2x and I divided a 2 out of pi. And if you were to multiply this back, 2 times x is 2x, 2 times pi halves is just pi. But you can see now that it's in this form, I have my b and my c. Because a lot of students did this. They wrote, oh, it's pi units to the left. Well, no, it's not pi units to the left, because when you factor out the 2, you can see it's pi half units to the left. So it's a very, very common mistake that students. So we just got to make sure we're writing it in that format when we're identifying the phase shift. Now, as far as the period goes, if in this form or this form, b is still 2. So, a lot of students still got the period correct, which is just, again, 2 pi divided by b. So I just do 2 pi divided by b in this case, which is pi. But you can see our phase shift here is going to be right pi halves. I am not adding or subtracting anything outside of the function, so there's no vertical transformation, but you can see I'm multiplying by a negative on the outside, so that is going to be a reflection about the x-axis. So we'll say reflect the x-axis. All right, so let's go ahead and go through what all these transformations are doing to the graph. So therefore, we can identify the domain and range. Now, if we just want to kind of go off of our knowledge, we know that the domain, doesn't matter what the transformations are, the domain is going to be negative infinity to infinity. So I kind of got that one in my back pocket. I don't really need to worry about that. But as far as the range, the only thing that's going to be affecting the range is going to be the amplitude as well as the vertical stretching or compression. And what we notice here, well, the amplitude, even though it's -1, like its absolute value of -1, it's still 1. So, let's just graph the cosine graph real quick so you can kind of see has the same period, it's 2 pi. Now, obviously, this is the initial period, not the new graph, because that graph got compressed to a period of pi, which I'll cover as well. Or at least I'll show you what that graph looks like. But let's just do the initial period here. So initial period of the parent graph goes like this. Okay. Now, the important thing, the reason why I wanted to show you this is the graph is not being stretched or compressed at all. The only thing that's happening with the graph is it's being reflected about the x-axis. And if we look at that, when you reflect this graph about the x-axis, notice that the amplitude, or not the amplitude, but notice that the range did not change, right? So this reflection about the x-axis is not going to be changing the range at all. And then obviously, since we have no more vertical shifting at all, then we're done. Like the range is just going to be from -1 to 1. All right, now let's go and sketch this graph because obviously the graph does not complete a period within 2 pi. The graph got compressed, right? So now the graph is completing a period between 0 and pi halves. So the graph is being compressed right? And then also, instead of the graph starting at 0, now the graph is being shifted pi half units to the right. So it's actually, my final graph actually would look something like this. My computer is being slow. Oh, crap. I forgot to plug it in. Shoot. So anyway, so we'd have pi half, so therefore this graph would actually look like this. That would be the final graph. Okay, so it's basically only has a period of pi, which in this case is from pi halves to 3 pi halves, and then it only has a period of pi. So that's what the graph looks like. But again, you can see that that period or that range is still from -1 to 1, and therefore that's where we get the range. And obviously we have also a reflection, but that doesn't change anything. All right, so let's go and look at the tangent function, which is again the same thing that is going on with the tangent function is, the same transformations that I talked about up here. Just replace the sign with tangent. We still have the A, B, C, and D. However, there are some changes here that are going on. The changes are now we have asymptotes, because if you remember when we looked at, this graph of tangent, that tangent when looking at the unit circle is y over x. Right? And that didn't happen for sine and cosine. And a lot of students gave me equations for asymptotes for sine and cosine, which doesn't make any sense because there's no undefined values for sine and cosine. But when we're dealing with tangent, since tangent of any angle is going to be y over x, any time that the x coordinate was 0, then we were going to have a asymptote. -1, 0. Okay? And you could see that that occurred at pi halves, at 3 pi halves, and that would continue going down. And we'll go over the parent graph, in a second once I get through the transformations. You can notice here, though, when I'm looking into identifying my A, that's easy. That's just a 1. But identifying the B might not be so easy. So what we want to do is, again, just think about you're dividing by 2. But remember, dividing by 2, like 4 divided by 2, is the same thing as multiplying by 1/2. Right? So what we're going to want to do is pull that 2 out in front and rewrite this as tangent of -1/2 x. Now you can see that this b is in front, and it's negative. So since it's negative, that means we're going to have a reflection about the y-axis, not the x-axis. X-axis is outside. The y-axis is multiplied by negative on the inside. We also can see that that 1/2 is going to be horizontally stretching the graph, but also affecting the period. Now, a lot of students confused, again, the period with tangent and sine and cosine. Remember that sine, cosine, cosecant, secant all have a period of 2 pi divided by b, whereas tangent and cotangent have a period of pi divided by b. There's also not an amplitude for tangent because the definition of amplitude is the half distance from the max to the min, right? And you can see on this cosine graph, it has a maximum point and a minimum point. Well, when we look at the tangent graph, you'll notice that it doesn't have a max and a min, so there is no amplitude. And that is the same case. That is also the case for the cosecant and secant graphs. All right, so then the easiest thing we're going to do right now is just look for the period. So I'll just write the period. Now the period is, again, pi divided by b, but period represents a distance, basically how long the graph repeats itself. So we don't really need to include the negative. We can just include the positive value because we're looking for a distance, not a direction. So pi divided by 1/2 multiplied by the reciprocal on the top and the bottom, and you get 2 pi. You can see I'm not adding or subtracting anything inside of the function, so there's no phase shift. I'm not adding or subtracting anything outside the function, so there's no vertical transformation. The only other thing that we have going on is a reflection of the y-axis. And that's all you really needed. You had a period, which I forgot, like my D there. Or my O, I just read period. Let's fix that. I-O-D. Okay, so my period, that doesn't look like a D. There you go. Looks horrible. That's okay. So my period is pi divided by b equals pi divided by 1/2 equals 2 pi. And then I'm reflecting my y-axis, and that's it. So let's go and look at the initial period of tangent, which we used from these points. Again, we can see that at the angle 0, y over x is 0. At the angle pi halves, we have an asymptote. At the angle negative pi halves, we also have an asymptote. And then what we did in class is we actually evaluated for the rest of the points. And so therefore we could see that the graph took the form, shape of something like that. Okay, so again, now the nice thing about the tangent and the cotangent is we already kind of know the range, because obviously the graph is going to continue indefinitely going down as well as up. So the range is fairly easy to write out. The range is going to be negative infinity to infinity. All right, now the domain is a little bit more difficult because we have to understand where the asymptotes occur. So let's just talk about where the asymptotes are. So again, we can see the asymptotes occur when the function is undefined, which occurs at pi halves. The next time it's going to be undefined is at 3 pi halves, which is pi away. And then if we add pi again, we'd get to 5 pi halves where it's undefined. Add pi again, we get to 7 pi halves. So you can see that every single time we're adding pi, we're getting to an asymptote or subtracting pi. So in our notes, we gave the general equation for the asymptote of the parent function. I'll do this in purple. To occur at x equals pi halves and then plus pi. But since we can add pi infinite many times or subtract pi infinite many times, we'll do pi times n, where n is going to be nth integer. Now, if we need to figure out, we have some transformations here, right? We're horizontally compressing this graph as well as a reflection. Now, the reflection is not really going to change anything. Like, notice when I take this graph and I reflect this about the the y-axis, you can see that the asymptotes are going to remain the same. The x-intercept remains the same. Like, nothing is going to be changing as far as this graph, except for just the shape of the graph, but the asymptotes remain the same. So I could include the negative if I wanted to, but I didn't mark anybody down if they did because there's nothing wrong with it. But we don't need to. The only thing that's going to affect the asymptotes is the 1/2. So I simply just set 1/2 x equal to pi halves plus pi n. And now I get rid of this 2 by multiplying everything by 2. And when I do that, I get x is equal to pi plus 2 pi n. So my new asymptote is x is equal to pi plus 2 pi n. Okay, so now what you can see is my asymptotes are occurring every pi. Like if n was 0, I'd have an asymptote at pi instead of at pi halves. So this graph is being stretched, right? And I didn't really leave myself enough space here, but you can see that now the graph is going from pi to negative pi. So now the graph is like whoosh. Yeah, get it fixed right in there, right? It's being stretched that way. So now I did ask for the domain, which again, the domain is going to be all real numbers except for where the asymptotes occur. So then I did write an example on the board for you to follow, but that's just all real numbers such that x cannot equal pi plus 2 pi n. All right, I need to, well, let's figure this one out, and then I'm going to take a break, and then I will get to some of you guys' questions. Thanks, I'm a dork. Yes, I am. It's a Sunday, and I'm doing math videos, but whatever. So anyways, I'll go and get your questions, and then I also need to get my charger because I forgot to plug in my computer, so it's going to die before I get to the second half. But anyways, I think I have enough juice, hopefully I do, to do this last problem. Now, this is the cosecant function, and the cosecant function, remember, is the reciprocal of sine. So the best way to understand this is to, what we did is we looked at the unit circle and understand that cosecant of any angle is just 1 over y. So again, we're going to have asymptotes here when the y coordinate is equal to 0, which we can see occurs at 0 and as well as at pi. But a better way to really understand this is going to be by looking at the reciprocal function, which is the sine graph, because the sine of x is just equal to the y coordinate. So let's go ahead and just sketch the y sine graph. Yeah, okay. So we'll go from 1 to negative 1, and let's go from here to here to 2 pi. And then we'll go pi. So that graph, sine graph, looks like this. Okay, so what we talked about again is if we know these are reciprocal properties, what we looked at is whenever the sine graph was 0, you could look at it by via the unit circle or by this graph, that the cosecant graph is going to have an asymptote. Okay, so we have asymptote here, asymptote there, asymptote here, asymptote there. And then we looked at some of the points to understand that this shape of the cosecant graph, and again, this is just the initial period, I haven't done any transformations here, is basically just the reciprocal kind of mirrored image of the sine graph. And I'm just sketching this graph so you have a visual understanding, and then also so you can understand that if I was to think about this in terms of like y equals 1/2 sine of x, like what is happening to the graph? The graph is going to be compressed by 1/2. It's not shifting up or down. It's not shifting left or right. It's not being reflected. It's not horizontally stretched or compressed. The only thing that's changing is the graph is being compressed. So instead of going up to 1, it's now only going up to 1/2. Instead of going down to 1, it's just going down to negative 1/2. So now the graph is going to look something like this. And again, I'm just going to dot this because this isn't part of the graph. We're just using this. Now the asymptotes, notice as I stretch this, that doesn't change where the asymptotes occur. So as long as I understand where the asymptotes occur, then I could go ahead and rewrite that from this. All right. And again, by understanding this graph, by understanding that cosecant is undefined at whenever y is 0 via the unit circle or this graph, you can see that the asymptotes occur at x equals 0 plus pi n. Or in our case, we just say x is equal to pi n. So I'll write that as an answer. The asymptotes occur at x equals pi n because no transformation that we did affected those. And then the other thing that's going to happen here is that, what else? Oh, so we can find the domain. So the domain is going to be all real numbers such that x cannot equal pi n. My computer is going to die. All right, we'll get there. And the last thing we need to do is talk about the range. So When we look at the sine graph, right, this graph is contained between -1 and 1. And you can see that the reciprocal relationship is basically like that mirrored image. So the parent graph is from -infinity, as you can see, from -infinity to -1, and then union 1 to infinity. However, since the graph got compressed, you can see that now the maximum value of my cosecant graph is -1/2. So when I'm writing my range, it's going to be from -infinity to -1/2. Notice -1/2 is included, so I'm going to use brackets. And then I'm going to connect that with 1/2, comma, infinity. Boom. And that's basically all we needed to do. Oh, the period. So again, the period is of the cosecant graph. It takes every 2 pi for it to repeat. And you can see that obviously my b in this case is 1, so I'm not going to have any changes in my period. So therefore, that's just going to be 2 pi. All right, so now what I'm going to do is I'm going to grab a charger, and then what I'll do is charge myself up. You guys can go ahead and look at the multiple choice questions if you want to, and then I will get into the chat and say hi to some of you guys for joining me. So I will be right back. Yeah. Okay, back in there. Let's go and say hi. So I had to move my computer because I left my extension cord doing some other work. So either way, it's going to be kind of odd because I'm going to have to turn, kind of close over here. But at least I have power, and at least we can go ahead and continue the stream. So let's just go and see. I was studying the same thing. Rahman, awesome to see. Robin says, can we have a lesson for conic sections of parabolas? Well, I don't have my playlist linked here as far as live streams that I've done. We're not going to get into conic sections here for another couple weeks, probably not until the fourth quarter of our period. However, I did start doing these live streams last year, at the end of last year, and I am almost positive that I covered some homework answers on how to do our conic section. So I did like homework answers, quiz answers, just like that. So what I will do is, because one of my goals, tasks for today was to split up my playlist, because right now all of these live streams that I'm doing are broken into playlists. They're just called my live streams. Pretty catchy, right? But what I want to do is go ahead and break them up into homework answer live streams as well as quiz answer live streams. So therefore, any of you guys that are watching this that are maybe just starting pre-calculus or algebra 2 or college algebra or trig, calculus, you can kind of go through and kind of see from the start to the end all of the homework that I gave, all of my quizzes, and kind of follow it in a sequence. I just haven't broken them up yet. So what I'll plan to do here for you is I will do that. I'll put them in the 2 different links, and then what I'll do is I'll add them into the description here. So therefore you can just go and follow those. And I'm almost positive from last year I did that for parabolas. And Kristen says, can you talk about matrices? I would love to talk a little bit more about matrices. Unfortunately, we don't cover matrices in our curriculum. And so it's just not something we really get to. And, that's obviously, that's a very important topic, once you get into like linear algebra and all that kind of stuff. And obviously, for a lot of the math we could do that further extension into the matrices and exploring that. And it just kind of stinks that they leave them out. And as far as the pacing, as far as the content that I need to deliver, I'm just not able to do that. Now, again, to your point, though, that is something that I would like to start doing like an addition like outside of school. And unfortunately this year I'm just not going to have, I just don't have the time because all the curriculum that I'm covering right now is taking too much of that time. But what I do plan on doing is getting into, oh, there's my pen. Once I'm done with this pre-calculus curriculum is then being able to do some supplemental curriculum, because obviously some people are taking, this course and they are doing problems with matrices. So since I don't teach that, that is something that I'd like to create for you. So Destiny, you have a Merry Christmas. I hope you have a great Merry Christmas as well, Destiny. I'm actually not interested in this. Well, no problem, son. That's why I do these live streams for people that interested for the stuff, then can watch, and then obviously you can always come back later and see for you guys. So this is obviously this is just for the pre-calculus curriculum, so I have anywhere from 10th graders to 12th graders in the class. So all right guys, well I'm just going to knock out these 1 2 3 4 5 multiple choice problems. Now you can see obviously we're making a transition here from the graphing to the inverses. All right, so completely really different topic. This is actually the last thing that we discussed in our notes. Last thing we discussed for the notes, and the first thing to kind of start off is immediately with the composition. Now I can actually go. Let's actually go from here. Let's understand question number 8, and then for any of you that's this kind of like new, this will kind of be a segue into what we're doing next. So I'll do number 8 and 9 first. So this one's saying the sine inverse. And the sine inverse function is basically our way to be able to undo sine. So another way to like think about this is, what are we asking? Well, when we're taking the sine inverse, we're looking for the angle. So another way to write this would be the sine of theta is equal to square root of 3 over 2. So they're saying, the sine of what angle equals the square root of 3 over 2. But the important thing is this is a function. It's not we're not like finding the solutions to an equation. We're actually using the inverse function, just like how you would undo, if I had like, x plus 1 equals 5, we would use the inverse operation of addition, which is subtraction. So the inverse operation of sine, because remember this is sine of, right? Sine is a function being applied to theta. So if we wanted to undo sine, we would use the sine inverse. So again, this is important. This is an inverse function. And the other important thing to understand about inverse functions is they have to be one-to-one. And none of our trigonometric functions are one-to-one, so therefore they are restricted. Now, I'm not going to get into the painstaking details of all those restrictions and why it works, because that is something that cannot just be like explained and understood. Well, I mean, it could, but for many students that are like trying to conceptually understand it, giving you like a 2-minute explanation doesn't really work. So I'm just going to restrict on the restrictions of the sine and tangent when using the inverse is restricted in the first and the fourth quadrant. And for cosine of x is restricted, or x is going to be restricted between 0 and pi. And the reason why, that's important, because again, if you were to type this into your calculator, like if you type this in your calculator, you can only get one answer. But we know initially by the unit circle here, sine is equal to square root of 3 over 2 for 2 answers. Over here and over here, right? Which is pi over 6 and, I'm sorry, making my mistakes. Slow down. Which is at pi over 3 and 2 pi over 3. So you can't plug this into your calculator and get 2 angles where the sine is both going to be the same, right? So we have to follow, and that's why we have followed these restrictions, right? And these are just going to be implied restrictions that are universally used. So by using this restriction, we can see the only angle that works is going to be pi over 3. All right. Again, in this next example, we're looking for tangent theta is equal to -1. Again, another way to look at that is tangent of theta is equal to -1. So the tangent of what angle equals -1. Tangent of what angle is equal to -1. Now again, it has to be in these first quadrants. Well, we know tangent is only negative in the second and the fourth quadrant, right? So since tangent is only negative in the second and the fourth quadrant, obviously the restriction of tangent inverse has to be in the fourth quadrant. So now we got to think about, well, then what angle makes it -1? What angle on the unit circle when we take the y coordinate over the x coordinate gives us -1? And hopefully you have a lot of experience with the unit circle at this point, and you know that that's going to be pi over 4. But since it's a -1, it needs to be in the fourth quadrant, so therefore it needs to be -pi over 4. All right, so now let's work our way back up to the composition, okay? So the composition is basically just like one function plugged into another function, all right? And if you did composition of functions, just regular functions, and we had to evaluate the composition, we always evaluate from the inside out because we followed our order of operations. And that's the exact same thing here. We're just going to work from the inside out. So the first thing we want to do is evaluate the cosine of negative pi over 3. Now, I've talked about the unit circle and evaluating points on the unit circle a lot in my class, so I'm not going to go through that. Let's just see here if I can do it, talk my way through it without making a mistake myself. So the cosine, forget about the negative for a second. The cosine of pi over 3 is going to be pi over 3, cosine of pi over 3 is 1/2. Since we know that's negative, then we know that's going to be in the fourth quadrant, where cosine is still positive, right? It's a negative angle, but it's in the fourth quadrant, where the cosine value, which is x on the unit circle, is still positive. So therefore, I can rewrite this as the cosine inverse of 1/2. And then I look at the cosine inverse of 1/2. Well, obviously there's two angles. There's one in the first quadrant, one in the second quadrant, but based on our constraints of cosine inverse, it has to be in the first or the second, so therefore my only answer is pi over 3. For the next one here, let's do this one, then we'll go through that one. So here we have cosine inverse of 1. So looking at the unit circle, what is the only angle that gives me an x value of 1? Now, fortunately, I don't even need the restrictions here because there's only one value on the unit circle where the x coordinate is equal to positive 1, and that is at 0. So therefore, I can just write that as tangent of 0. Now, again, going back to the unit circle, remember tangent is y over x. Well, when x is 1, that means y is 0. So it's 0 over 1. So therefore, the answer is 0. All right, for this next one, we don't recognize this point from the unit circle, right? Now, we don't know if it's on the unit circle or not, but the important thing is we just don't recognize it. So if you remember, the unit circle is made up special right triangles, right? It's made up of triangles, but it's restricted, or we have our restriction based on the special right triangles. So this could still be a point on the unit circle. We just don't know any other values here. So what we're going to need to do now is then create a triangle to represent this relationship. So if I was going to have this relationship as a positive 4, positive 7 on the opposite and adjacent, then I can represent the tangent inverse of 4 over 7. Now, to evaluate the tangent inverse, since I don't know this value on the unit circle, I can't use the unit circle. I can't find the angle like I did over here. Like the cosine inverse of 1 is 0, right? I don't need to plug that into a calculator. I know what that value is. Here, I don't know the tangent of theta, tangent of what angle equals 4 over 7. I would actually need to use a calculator. But the nice thing about this composition is actually I don't need to find the angle. All I need to do is I use this to set up my triangle, and now I just need to take the cosine of this unknown angle, right? So I did this to create the relationship of theta, but now I just need to take the cosine of this theta. Well, I can take the cosine of this triangle. I just need to figure out what the hypotenuse is. So I have 7 squared plus 4 squared equals my hypotenuse squared. Let's just call it r squared. So this is 49 plus 16 equals r squared, and I can do r equals 49 plus 16 is 65. Square root both sides, that'd be 65. So therefore, the cosine of that angle is going to be 7 over the square root of 65. And when you simplify that, you would get answer B. So I believe I covered all of my answers. So sweet. There you go, ladies and gentlemen. Again, just a reminder, guys, I will be looking into doing a live stream here at, I believe I'm going to plan on doing it like on Wednesday and I have, I think, 45 questions that I'm going to work through, and that's going to cover everything that we've covered in pre-calculus, from functions to polynomials to rational functions to trigonometry. But that's where we end. And then obviously into the new year, 2019, we're going to get started right with analytical trigonometry, dealing with our identities. And then we'll get into the fun stuff, oblique triangles, parametric, polar, vectors, and then lastly, conic sections and limits. So good to see you guys still hanging out onwards. See if you guys have any questions, anything about I covered in this, or in your own classes maybe you have coming up on your exam. Feel free to let me know. I'll be happy to address this. Anwar says, right now we are learning about transformations and reflections of quadratic functions. Can you explain that? Because I don't get it when the teacher explained it to us. Anwar, if you have any more details that you have, I mean, I can go ahead and give you a very basic understanding of like reflections, and then I can also give you, or I could go in a little bit more advanced, but I'm not really sure the context to of what you're having trouble with or what you would like explained. Either way, I can give you something, maybe it'll help, but if you have any other additional details of what you're having trouble with, then that would help me out. Please discuss continuity. My son needs help. Hey, Denise, my son needs help with algebra. Well, if you guys have any questions, like I said, I mean, this is kind of my time having a little fun. My kids are both down for their nap, so, and then my wife is running some errands with her mom, so just kind of hanging out with you guys for there. So if you guys have any questions on there, go to help. So please discuss continuity. Well, I mean, I'm not sure, Anthar, if you have any like specific questions on continuity. I mean, the basic understanding of continuity is a graph that does not have any breaks or holes in it. So, you know, if you can sketch a graph, if you can sketch a graph without any breaks or holes in it, it is continuous. But anytime that you have something like a vertical asymptote, well, that is a break. The graph does not, you know, connect. Or if you have something where there's like a hole, then it's not continuous. Obviously, we can identify continuity using like piecewise functions, and I'm not sure if that's maybe you're getting at a little bit more of calculus into this. You know, how to determine if something is continuous or not. But, you know, that's just the basic understanding of continuity. Make a video for algebra word problems. I do have some videos on algebra word problems. That's kind of hard for me to be able to make up though on the fly as far as some word problem. But I want to get back to learning transformations. So, I mean, I'll talk about the transformations. Let's just look at, what is it? How we learn about transformations and reflections of quadratic functions. Yeah. So, I mean, the nice thing about this, even though, you know, this is I mean, the best advice that I can give you, Anwar, as far as transformations, is go to Desmos.com, because Desmos.com is awesome. I mean, I can give you, you know, what you can do here, but the main important thing is, like, when you have y equals x squared, that gives you what the parent graph is. And that parent graph, if you were to create a table of all x and y axes, you can see is going to look like that, right? But the cool thing about that is now there's all these transformations. Y equals a times x, you know, minus c squared. We're not going to worry about the b for quadratics, plus d. And what you can do is you can plug in numbers where a, c, and d would be, and you can see what is going to be, what is affecting the graph, why it's affecting the graph. And then you could also like look at, you know, table of values. So when we teach this like in Algebra 1, a lot of times we look at, you know, the table of values, choosing values for x, finding the values of y. But I think the easiest thing to do in this case would just be going to Desmos and play around with it. And if that's something you want me to do here at the end of the stream, I can go ahead and do that. You know, I'll be happy just to kind of like discuss about that as well. DC, happy to be able to help you out. Prove that f of x equals 1 over x to the fourth plus 7x squared plus 1 is continuous everywhere, carefully justifying each step. How do you determine the starting and ending point of a tangent for a horizontal shift? And there, I'm not sure, is that x in the denominator? Because then it wouldn't be continuous when x is equal to 0, or it's just not something I'm familiar with. Like, all right, I'll go and play around. I'll play around with the quadratics for you, Anthar. But is this what you're saying? F over x to the fourth plus 7x squared plus 1? Is that what you're looking at, Anthar? Please confirm before I can talk about that function. All right, I'll go ahead and do that. Let's go and talk about the starting and end, because that is something important. That's something I used to teach as far as the transformations of the graph. So let's look at the tangent function, and then what I'll do is I will go into Desmos and play around with that. So tangent, so for the tangent function, the initial period looks like this. So we have pi halves, and we have negative pi halves. like that, looks like that. So the graph, okay? So what we can say here is this is the start. So the start is at negative pi halves, and the end is at pi halves. So for instance, if, let's say I have y equals tangent of x, that's it. So the only thing we need to concern now, the only time the start and the end is going to change is when we have a horizontal compression or stretch, or we're shifting left and right. Any other time, like shifting up or down, reflecting up or down, stretching up or down, that's not going to change the start and the end. So the only time this is going to change is when we have transformations on the inside. For example, b times x minus c. That's the only time. The a and the d do not affect the start and the end. So how do they affect them? Well, all you're going to do now is just take your start, just take b times x minus c, and then set that equal to negative pi halves to find and then solve for x to find the new start. And then for the end, just take b times x minus c, and then set that equal to pi halves, and go from there. Ozymandias, can you talk about multiple answers or restrictions on inverse trig functions like problem 8? There could have been multiple answers. Yeah, I'll go ahead and discuss this. Please discuss this after this. So, I'm not seeing find the values of k, if any, which is not continuous. Okay, so, let's go ahead and identify. Now, there's a couple different ways that variables are going to be undefined. Now, it's important here that when we have okay, so hopefully that helped as far as the tangents. Obviously, let's just do a quick example. Why not? I got time. Let's do y equals, tangent of 2 times x minus pi. Right? So then all you would do is just do 2 times x minus pi is equal to a negative pi halves. So you divide by 2 on both sides. You get x minus pi is equal to negative pi over 4. And then you would add pi. And then you get x is equal to 3 pi over 4. Now, to save myself some time, if I was going to do that over here, I would have, then I'd do 2 times x minus pi is equal to a positive pi halves. And then I divide by 2, I get pi fourths. And then add that, so I did x equals 5 pi over 4. Boom. So there is the start, and this would be the end. Okay, so let's go and talk a little bit more about continuity. So you're asking basically, and you're talking about continuity basically on an equation form, but hopefully it makes sense to you as far as continuity in graphical form. Like a graph is not continuous when there is a vertical asymptote or when there is a hole. So let's go and investigate a little bit when these discontinuities occur, because these discontinuities, as far as vertical asymptotes only occur in certain situations. Now, I'm going to stay away from the logarithmic functions or other functions that would have discontinuities because it doesn't seem like you're dealing with that. You're basically dealing with a lot of other functions, not your transcendentals. So the important thing is the vertical asymptotes. Where does the vertical asymptote occur? A vertical asymptote occurs is when at least in this case, is when the denominator is equal to 0. So like for instance, if I had f of x equals 1 over x minus, I don't want to get into that, but let's just look at it here. A vertical asymptote, well, I don't want it to, here, all right. I don't want to confuse when people look at these notes, think that's the function, because that's not the function. But you can see that a vertical asymptote is going to occur when we have a x in the denominator. Over here, a hole is going to occur usually when we have a piecewise function, when there is a defined value that is undefined. So basically, I can give you a piecewise here, and a rational function is going to give you a vertical asymptote. Okay, so hopefully that's going to kind of restrict our understanding here. Now, if this is your function, you notice that we have x in the denominator, right? So we got to think, well, what values then is going to make our denominator equal to 0? Because whatever values make our denominator equal to 0 is going to be undefined. And therefore, we can say that this graph is not continuous because x cannot equal 0. Now, there's another one that you gave me, which is f of x is equal to 5x to the fourth. And I'll plug these into Desmos when I get into Desmos so you can see. 5x to the fourth minus 3x plus 7. All right, is there a chance for us to divide by 0? No, there's no variable in the denominator. And then is this a piecewise function where we have some values that are undefined? And no. So guess what? This is continuous. There are no values that are undefined. So we just write continuous. All right, so what I'm going to do is I'm just going to talk about the trig functions here real quick, and then what I'll do, guys, is I will get into Desmos, and I'll show you guys a little bit more about the transformations, because I think the transformations actually ties very much into, this unit as far as what we talked about. And then also I will plug these two functions in there as well to explain that. All right, so I lost my train of thought. Oh yeah, let's talk about the restrictions. So you're talking about on question number 8. Let's look at question number 8 real quick. Question number 8, sine inverse the square root of 3 over 2. All right, so that's the sine function. So we know the sine function looks like this. Right, so there it's at 2 pi, and then this graph continues going. Right, so let's actually continue it, and then also goes in this negative direction as well. So it's kind of confusing. And this is actually what we talked about in my class. And let's look at also over here when we're looking at just the unit circle. So when we're looking at the sine is equal to square root of 3 over 2, we know that occurs at pi over 3, because this point is 1/2 comma square root of 3 over 2. And then it also occurs at 2 pi over 3, because this point is negative 1/2 comma square root of 3 over 2. So these are both two answers. Like to the question, sine inverse of square root of 3 over 2. If you notice, we have two answers. But the issue with this is you can't plug this into a calculator and say, oh, I have two answers. But again, that's just two answers of the initial period. That's just two answers between 0 and 2 pi. When we look at the graph, so we know it's at pi over 3, right? So pi over 3 is going to be like, here's pi. So here'd be pi halves. So when we're looking at this now, when is the sine inverse going to equal to pi, or for what angle does it equal to square root of 3 over 2? Yeah. So that's going to be like right here. Now again, it's equal to pi over 3 and 2 pi over 3. So let's just say here's pi over 3, and here's 2 pi over 3. Well, guess what? It happens again here and again here. It's going to happen here. And there's infinite many answers. So when we look at this, we're like, oh, crap. Like, there is infinite many answers here. That's going to be a problem. So, because if we're trying to work backwards, we're trying to use the inverse function, you can't plug into your calculator and get infinite many answers. So what we need to do is we need to restrict this. And what I talked about in my class is we did this before. Y equals x squared is not a function that is invertible, because when you reflect this about the y equals x line, you get a function that does not pass the vertical line test. So the only way we can get around this is to add restrictions. So when we go ahead and add restrictions, what we'd do is I'd say y equals x squared, but x has to be less than 0. So we add a restriction. And what that does is that allows us now to evaluate or to create the inverse. So now I can just reflect this about the y-axis, and now that works. Now the problem here is, again, I just chose that restriction. And again, there is no like implied restriction for quadratics. It's basically, it's not invertible unless there is some restriction that is applied. However, the inverse trigonometric functions are actually functions that we have defined and we have an implied restriction on them. So then what is the restriction? Like, how is these restrictions, defined? So basically, like, how can I restrict the graph like I did for, x squared? But the problem is these graphs go on and on forever, right? So we have to find some interval that we want to restrict the graph. And we have to define that interval where the graph is going to be 1 to 1. Because again, if the graph does not pass the horizontal line test, then it's not going to be invertible. So for instance, I don't want to pick the restriction 0 to pi because that doesn't pass the horizontal line test. So what is decided is to be from pi halves to negative pi halves. That is going to be the restriction. So that is why, and you look at this, when I looked at, the point, when we look at this as far as on the unit circle, that's why we say the restriction, or we're given a restriction of negative pi halves to pi halves. So when we're talking about find the sine inverse, technically we're basically like find the sine inverse when, sine is, restricted from negative pi halves, or we could say, sine of whatever your angle, is equal to square root of 3 over 2, and that is restricted from negative pi halves to pi halves. We just don't write in that restriction like we do with the quadratics because it's implied. All right, and the tangent and the cosine all have those, again, implied restrictions, and that's what's built into, that's what's programmed into your calculator. Because again, if we didn't restrict the angles for sine, we would have infinite many answers, as you noted for me, right? So that's why we have to follow those restrictions. Otherwise, we wouldn't be able to plug it into our calculator and get one answer. All right, so I think that's, can you try transformations? Sure, I'll talk about it, transformations. It's going to be exactly the same thing. David, do you have the basic number theorem? Unfortunately, I don't, but that is something I would love to go ahead and get into. But unfortunately for this, I just don't have the time or really the resources yet up there. So, all right, so let's go and talk about exponential. We can talk about quadratics. Actually, let's see. Oh, did I not pick up Desmos? Let's see if Desmos will pop up. Sweet. Oh, all right. So let's see. All right. So let's go ahead and pick a example here. Y equals x. Or let's do y equals x squared, and y equals a. Let's add a slider. A r squared. Oops, sorry. X minus c. Squared plus d. Add a slider. Okay, so there we go, C. There you go. And then we can do this exact same thing for exponential. We can do y equals, e raised to the x. And then we can do y equals a times e raised to the x minus c. Oops. Minus, come on. And I'll improve this. And then plus d. Let's close that down for a second. I want the RE. Oh, that's doing it for the same one. Okay. so I guess the same slider. I didn't know that works like that. Cool, Desmos. X minus C plus D. All right. So again, we want A here to be 0. And guys, I'm going to have to shut this short because my youngest is now up. So, but either way, hopefully you guys can type in basically exactly what I have here. Here is the parent function. And then guys, you know, as we look at this, as we do a slider for A, you can see here, there you go. As A is positive, you can see like here's A when A is equal to 1, right? Same thing. But now as I have that number in front get larger and larger, you can see what that's doing. That's vertically stretching the graph. Or as it's between 0 and 1, you can see it's horizontally compressing the graph, and then as it gets to negative, it reflects. So whenever we're multiplying by negative on the outside, it's a reflection. And again, like you can see, that's the exact same thing that happens with an exponential, right? So as this number gets larger and larger, it's vertically stretching it, also changing the y-intercept. As it gets between 0 and 1, you can see it's horizontally compressing the graph, and as it gets to negative, it reflects it. And again, it doesn't matter what function I give you. These transformations, that A is going to have the same impact. Now we can look at, let's look at now C. C is again our horizontal shift. So what we have here is when we're dealing with this, oh geez, okay, add a slider A, fine. So we're looking at A, yeah, A is 1, that's cool. All right, but you can see now, C, as I'm shifting this graph to the right and to the left, you can see it's shifting, it's moving the graph to the left. So as C is x minus 3, as x is equals 5, you can see it's moving to the right. When it's negative, that would be x minus, like a negative 1, which would really be x plus 1. You can see it's moving to the left. And again, I don't need to use this function. I could use the quadratic, right? When C is negative, you can see it's moving to the left. And again, that would be x minus negative 2.4, which is written as x plus 2.4. And then we can shift, again, going to the right as well. So that would be like x minus 3.6 because C is going to be positive. And then last but not least, again, for either function, D is going to be shifting it up or down. So when it's positive, okay. So you can see as this is, why is A? I don't want that to be negative. Okay, so you can see it's moving the graph up or down, right? And the same thing would happen with my e to the x function. As I'm shifting this, my D is again just shifting the graph up or down. Okay, and obviously this graph is being shifted out to the right, but hopefully you guys go ahead and get to the version from there. So either way, guys, I am going to have to sign off for the rest of the day. I'm sorry, my obviously phone calls. And then my child's up, so we're going to have to end this up. But I do appreciate you guys asking some questions so I could do something besides what I'm just covering in class. So I do appreciate that. I'm hoping I was able to help you guys out. Obviously, when I do my last live stream, you know, make sure if you guys have some questions, I'll be happy to spend some time doing that as well. And I apologize to any of you that got into the chat. I wasn't able to get some of your questions. And David, I see that you're talking about different lines that have the same slope are parallel. And again, if they have the same slope, that means they're increasing. Their rise and their run is exactly the same, kind of like train tracks. So they're just never going to cross. But again, that's something I can get into more detail with you, next live stream, which again, tentatively, I will plan on doing that on Wednesday. So either way, guys, hopefully you have a great rest of your day, and I'll look forward to checking you guys on the next stream. Serious. No, that was supposed to work. Oh, it doesn't like it like that. Okay. Well, then I will just... I don't know. I was trying to